Hello again everyone, welcome back to ptet.chemistry channel. My name is Dr. On, and in this tutorial video, I'll go through these 9701s. This is from June 2015. This is paper 4 variant 1. So from the older syllabus, so prior to 2016 revamp, we used to have section A and section B. So of course there are some stuff, there was quite a big revamp, that there was some stuff from the old syllabus, they are no longer relevant to the current 2022 specification, for example. So I will inform you as we go through the paper, and there will be some biochemistry question in the section B that will totally not be relevant to the new specification anymore. So in this first question, complete the electronic configurations of the following atoms. So these are straight AS level electronic configuration. If you have oxygen, you know that this is period 2 and there's group 16. So we're looking at 1s2, 2s2, 2p6, and period 2, so there's 2p4, so 2 plus 4, 6 electrons in outer shell, group 16. Fluorine is just next to oxygen, so it's 2s2, 2p5 is 1 electron short from a fully filled outer shell. In the second question, a compound of fluorine and oxygen contains 3 atoms in each molecule. So if you think about fluorine, so this is going back to your O-level or IGCSE level or GCSE level chemistry in terms of 2-7 electronic configuration, just a really simplified configuration. We look at the number of outer shell electrons, and then valency is what you call the combining power. So we're looking at valency of 1 and valency of 2 because these are how many electrons each of them need to share to complete the outer shell. And then you do the crisscrossing. That is basically the lowest common multiple of the valency, LCM, primary school mathematics. You need 2 of the fluorines, this thing here, fluorine, 2 of them, and you need 1 of these oxygens, such that your formula is going to be F2O. If I draw the dot and cross, before I do the dot and cross, I'm going to draw the display formula. So it looks like water. Instead of hydrogen forming a single covalent bond to hydrogen, you have fluorine, the group 17 halogens that form a single covalent bond to the group 16 oxygen there. So predicting its formula, F2O, drawing the dot and cross, this is not dot and cross, this is simply a display formula. But looking at the single covalent bond, that is a dot and a cross. Looking at the other single covalent bond, there's a dot and a cross, but we gotta show all the outer shell electrons, even though when the question doesn't say dot and cross means show all the outer shell electrons. So if I do crosses on the oxygen, I started with 6 crosses, 1 2 3 4 5 6, and I share 2 electrons each from each of the each electron from each of these fluorine atom. I was going to say sulfur, but that was obviously wrong. And then fluorine, group 17, started out with 7 valence electron. You have 7 crosses, so 7 dots originally, and now you share 1 electrons, 1 cross from the oxygen. You now have 8 electrons around each fluorine. Do we have to draw these lone pair above and bottom? You don't have to. You can show the fluorine side by side, and you have the lone pair and the lone pair there. Doesn't matter because we know in 3 dimensions the shape of this molecule is going to be linear. Not linear. I don't know what I'm doing. It's not going to be linear. In fact, it has got 2 bond pairs, and it has got 2 lone pairs of electrons. So we talk about VSEPR as stated in the AS syllabus. Your lone pair will repel more than lone pair, will repel more than bond pair. Overall, you get this shape called nonlinear. And some books will say that this is bent. Some books will say that this is V-shape. This next question, we've got to predict relative oxidizing abilities of fluorine and chlorine. So this is not about going down the whole of group 17 halogens, but it's just fluorine and chlorine. So we're going to go to the E0 values in the data booklet. So in the current 2022 specifications, your paper 1 all the way to paper 4, well, excluding the paper 3, will no longer have the data booklet separate. Instead, it will be inside the question paper itself. So you probably not get a question like this unless the data in the questions, try to guide you like that. So we have E0 Cl2 Cl minus. We always represent this as reduction potential because all the electron potentials in the data booklet, they show you as standard reduction potential. So they are in alphabetical order. The Cl2 adding electrons to give you chloride, that is plus 1.36 volt there. And when I go to the F2, F minus, so further down, alphabetical order, that is plus 2.87 volt. So what can we predict about the relative oxidizing ability? We know that the halogens are oxidizing agent. So what do oxidizing agent do? Oxidizing agent oxidizes the other substance. So they oxidize others. But what happened to itself? Itself get reduced. Itself get reduced. That is the key factor there. Itself get reduced. Well, actually, there's number 1 and there's number 2. Supposedly, the number 3 actually follows from number 2. So itself get reduced. So more positive E naught for fluorine than the E naught than that of chlorine means fluorine prefers reduction more, as it favors the equilibrium more to the right hand side. It prefers to gain electrons more, it prefers to get reduced more, and therefore fluorine is the stronger oxidizing agent. So fluorine is stronger oxidizing agent because it prefers to be reduced more. So that is what the question really wants there. Predict the type of reaction that would occur if you have interhalogen compound, such that you have one chlorine and one fluorine with potassium bromide. So if you have something like chlorine and fluorine, you are going to imagine that your E naught, well, we don't know which one is going to be which one, but supposedly if you have ClF there, the ClF, when it get electrons, they can potentially get Cl minus and F minus like that, and then you have 2 electrons. But of course, we don't have the actual values, but what can we say? The value is going to be somewhere intermediate in between that of both of them being chlorine and both of them being fluorine. So they are saying what would be the value? Well, predict the type of reaction that will occur. That would occur means we're expecting it to occur if it does occur, and both of them are stronger oxidizing agent than bromine. So both of them can oxidize bromide to bromine. If you imagine the oxidizing power straight from AS chemistry, oxidizing power of the halogen, fluorine, chlorine, bromine, iodine, like that. So if bromine is below chlorine, that means these two are stronger oxidizing agent than these. So if you have something which is interhalogen, like F and chlorine, somewhere intermediate, is still a stronger oxidizing agent than that. So obviously you will get a redox equation where you will oxidize the bromide to bromine, and then this particular ClF will undergo reduction. Construct an equation for this reaction. So now they want an equation. So FCl plus KBr. First of all, we know definitely they will go to Br2 as that get oxidized. So Br0 to Br minus 1 in bromide, going to Br0 in bromine. I wonder what's going to happen to the FCl now. So if both of them FCl, this is going to oxidize that, and then this will get reduced. So what I'll get is F2 and C. Nope, I will get F minus and Cl minus. And instead of the usual 2F minus or 2Cl minus, I get 1 of each because I have 1 of that, and I need 2 of KBr, and that balances out the Br, and I will have 2 potassium, so it's Kf and also KCl, just to balance the equation. KCl and Kf, that is Cl minus 1, that is F minus 1, that is F. It's a bit hard to think about oxidation number here, but then because fluorine is more electronegative than chlorine, so what I can say is that must be fluorine minus 1, and the chlorine must be the one with the positive oxidation number, because fluorine is more electronegative. So going from chlorine plus 1 to chlorine minus 1, you can imagine that as a reduction reaction, and this is your oxidation reaction there. Let me see if that is all right. Yeah, that's probably the best I can do in terms of the information given, isn't it? Okay, so that's it really for these 8 mark questions on, well, actually quite a lot of AS halogen chemistry, but also quite a bit of this A2 electrochemistry there. In this second question, we have some organic chemistry. We have chloroalkane, so this is halogenoalkane, and we have acyl chloride, which is RCOCl. They each react with water, and that is a reaction you will call hydrolysis, but only acyl chloride fume in the moist air because acyl chloride is very reactive to hydrolysis, very sensitive to hydrolysis. The acyl chloride fume there, the fume is actually HCl gas. So which product caused the fumes? It is not hydrochloric acid, it's the hydrogen chloride. Hydrochloric acid will still be in solution. So if you write hydrochloric acid, you got to think about what hydrochloric acid actually is. HCl aqueous is not a gas. Acid is dissolved in water to give you H+, so that cannot be the answer there because it is not a gas, it's not the fume there. Explain why the reactivity of chloroalkanes and acyl chloride differ. For that 1 mark, we're going to think about the system here. So RCOCl, 2 highly electronegative atoms, oxygen and fluorine, versus halogenoalkane, so just RCl like that, delta negative, delta positive on the carbon. So what we can say is 2 highly electronegative atoms. So chlorine is not like in the top 3 of electronegativity, but you know, it's still halogen, it's still very electronegative. So 2 highly electronegative atoms, chlorine and also oxygen. Well, since I already started using symbol, I might as well use symbol. 2 highly electronegative atoms withdraws electron density from carbon in the acyl chloride. So your carbon become more susceptible. So that carbon becomes very delta plus, that means electron deficient, and therefore it would be very easily and susceptible to attack from the water, which can act as a nucleophile as you have lone pair on the water. Part B, so we have compound R. Compound R is this thing here, and is a useful intermediate in the synthesis of blah blah blah. You can make R from compound P. Compound P is a hydrocarbon, compound containing carbon and hydrogen atoms only, and from there you can get this carboxylic acid. We think about carboxylic acid bonded to a benzene ring as benzoic acid, and this is also benzoic acid. So this is a dibenzoic acid, something like that. So we can think about benzene chemistry. Which one will allow you to give you benzoic acid? It has to be the oxidation of alkyl side chain, and this is only possible when you do it in acidified KMnO4, and you have to reflux this. Okay, so very strong oxidizing agent there that can oxidize any long chain, any alkyl long chain on the benzene, and they will convert this to carboxylic acid and this to carboxylic acid. 6 carbon inside there, 7 and 8 carbons. So 4 hydrogen there, 1, 2, 3, and 4. 2 of them got substituted. Carbon from 4 bond, you only show 1, so there is a 3 hydrogen and 3 hydrogen, 6 hydrogen, 7, 8, 9, and 10. So you know, this will give you that. That started with skeletal formula. I'm just going to maintain with skeletal formula. I'm sure if you write CH3 and CH3, they will have been alright as well. Step 2, so step 1 just now was oxidation, was the type of reaction. Step 2, we're going to substitute the OH and become Cl. So these are acyl chloride, which are much more reactive compared to carboxylic acid to nucleophile. So this type of reaction, the type of reaction is going to be what you call substitution, because you are exchanging or replacing the OH with Cl, and typically you need something like SOCl2, or you can use PCl5 to achieve this thing to make acyl chloride in A2 chemistry. In step 3, this amine, this is 2 carbon amine, this is called ethyl amine, and they have lone pair on the nitrogen, this is the nucleophile, and then you have got delta plus on the carbonyl carbon of acyl chloride, very susceptible to attack on these by this nitrogen lone pair. So this is going to do a condensation reaction. It's a condensation reaction because you are going to form an amide. When you form amide, that reaction is called condensation. When you form ester, that reaction is called condensation. This is in AS Introductory Organic Chemistry syllabus, and you will see that the product is going to be O and then NH and then like that, CH2CH3. But my concern is, if you see this properly, you will see that there's only one nitrogen, and that is because after you do the first condensation on here and you kick out HCl, you are going to do a second condensation as you still have a lone pair there, and that lone pair can attack on this delta plus carbon, and it's going to do a condensation reaction where it does nucleophilic addition onto the carbon-oxygen double bond and then elimination of the Cl minus. Overall, what you're going to get will be without that thing there. So what you're going to get is the nitrogen is going to come together and they're going to link them together like that, and you will get the CH2CH3 here. That is why you only have one nitrogen there, because you do double condensation reactions, and this reaction will give out 2 HCl. As you do one condensation, give out 1 HCl. The second condensation loses the other H and the Cl as this steamy white fume. 6 carbons, 7, 8, 9 and 10. So 1, 2, 3 and 4 hydrogen, no hydrogen there. 5, 6, 7, 8, 9 hydrogen in this molecule, to 1 nitrogen and 2 oxygen. And from there you can get here, when you reduce amide, this is amide, this is not ketone because next to it is carbon, but next to it is nitrogen, CONH. In this case you don't have an NH because it's already been used to form these cyclic amide here. So this is an amide. This is also an amide. This is called reduction. The type of reduction is reduction of the amide group. And to reduce amide is in the A2 syllabus under amine and amide chemistry. You need things like LiAlH4, lithium aluminium hydride. You do this in dry ether and you reflux that. Okay. Suggesting the structures for the starting material P and the intermediate Q, I already gotten the 2 marks there. Suggesting reagents and conditions for the following steps for the last 3 marks. Step 1 was your oxidation of alkyl side chain there. So I have decided to use the acidified KMnO4. And also the conditions, because as stated in the question, reagents and conditions, do not forget that. The very next thing was step 2. We're trying to convert this carboxylic acid to acyl chloride. So this was the substitution reaction, and we can use things like PCl5 or SOCl2, or you can use PCl3 as well. The last one, step 4. Step 4 was this one, not step 3. Step 3 was substitution. They already provided you the reactants, and this was usually done with this in ethanol. This thing in ethanol is the solvent, and then reflux to make sure it happened. The very last step was reduction of amide. You need the lithium aluminium hydride, and this is in dry ether. I think, if I'm not mistaken, sodium borohydride can be used because it's not strong enough to reduce amide. Just like sodium borohydride is not strong enough to reduce carboxylic acid to alcohol, it wouldn't be strong enough to reduce the amide to amine, if I'm not mistaken. But we'll just stick with this because this is as stated in the syllabus. The reduction of amide, the reduction of nitriles to amines, both of them can use lithium aluminium hydride there. Okay, there's also another choice, if I'm not mistaken. You can use hydrogen and nickel catalyst, hydrogen molecule and platinum catalyst, and heat. That should also work to reduce the ketone there, as not the ketone, to reduce the amide as well. Okay, in terms of this PCl5 SOCl2, so you should be able to write an equation. This is just a general carboxylic acid that you can write with PCl5, and that should give you RCOCl plus POCl3 plus HCl. That will be your steamy white fumes. As this reaction progresses, you have got 2 carboxylic acid, so there and there. So when you have 2 carboxylic acid, you can imagine you have 2 of that and 2 of that, and you get a diol chloride because you get 2 times acyl chloride, and you get 2 of that and 2 HCl. How about when you use SOCl2? Similar kind of chemistry, so that thing plus 1 SOCl2, you're gonna get the acyl chloride as the OH get replaced with chlorine, and you get acyl chloride. Now the SO combined with the oxygen, you get SO2. And last but not least, you can also get the HCl steamy white film as your observations for this reaction. When you convert the OH of carboxylic acid into acyl chloride, both of these are done at room temperature. It's a very exothermic reaction. If you heat up any further, it might be dangerous in the lab. And that's the end of that 7-mark organic question there. In this third question, it started out with a mass spectrum. This is mass spectrum of this element magnesium. The fact that we see 3 lines, 24, 25, 26, and each of them have their own relative abundance. This must be 10 because there was 50 there. So 10, 20, 30, 40, 50. And that thing is just below 90 there. I think it's 90, 60, 70. Oops, I was wrong. That is not 90. Do not make my mistake. Oh, excuse me. So there was 50, which means it's 60, 70. So read that carefully. There's 80 there. So that's just below 80. And this is just above 10. If you look at that carefully, this is 10%. This is just above 10%. So without wasting so much time on it, I will just say estimate probably say 11% or 12. And this is going to be the difference there. So the difference there is just going to be, I don't know, 79% maybe. 79% if you're talking about 11%, or 78% if you're talking about 12% there. And you can see the percentage will add up to 100%. Of course, 79 plus 10 plus 11, 100%, or 78 plus 12 plus 10, that will give you 100% as well. So from the mass spectrum, complete the table with the relative abundances. So there's a 10% there. I think I'm just gonna stick with that looks more like 78 because it's a bit lower. But again, you don't want to spend too much time thinking about, 79, 78. At the end of the day, they're going to be roughly approximate unless they give you the value there. So the 26 there is going to be 12% if I use 78% for the top one there. Now use your values to calculate relative atomic mass given to 2 decimal places, and they are very stingy in A2 because they expect you to be able to do these kind of calculations in A2 already. The mass number multiplied by the percentage, so 24 multiplied by 78%, and then you add up with the other multiplications of mass number and the percentage, and you add up the other one, and then that whole thing in a big bracket. Make sure you use bracket to be careful. Divide that by 100%. What you will get then is 24 times 78 plus 25 times 10 plus 26 times 12. You get 2434. And you divide that by 100%. So you get 24.34 on your calculator. And that is exactly to 2 decimal place on the calculator. So I'll just leave it as 2 decimal place as it is there. If you look in your periodic table, you will see that this value is not very different from the one given in the periodic table because it's supposed to be very close to the 24.3 in the periodic table that you are given in exam. But of course, we cannot write 24.3 since they wanted to turn 2 decimal place based on our calculation. We are just confirming with our periodic table that our value is definitely correct there. In this next question, this is about a fixed essay for these 3 marks. It's a fixed essay because you can definitely prepare for this. Thermal stability of the group 2 nitrates. In the new syllabus, in the new specification, they will have changed this Roman numeral to this number here, group 2 nitrates. And it's the same trend with the thermal stability of the group 2 carbonates. So we just need to be able to prepare our essay. So first of all, actually, I'll probably explain first because it's a lot easier to explain first. Down group 2, what we can say is there are more filled electronic shell. So there are more electron shell essentially. There are filled. And as a result of it, we can get a bigger ionic radius. So ionic radius of the M2 plus cations, because we are talking about general group 2 cations, and these are nitrate, which is NO3 minus. Even year 9 student is expected to know the formula of nitrate ion. Ionic radius of M2 plus cations increases, the size gets bigger, but the charge is the same. So the charge remains plus 2. Overall, what you can say is the charge density, because charge density is to do with charge over size. So what you get is charge over size. Your charge is the same, but your size is getting bigger. So what we can say is, therefore, the M2 plus cations become less polarizing, or we can say the M2 plus cations are less polarizing on the anion, on the NO3 minus anion. And what does that mean? That means the NO bond become less polarized, and therefore it is less weakened. If it is less weakened, it means it is much more difficult to break. Therefore, much more difficult to break. If it is becoming much more difficult to break the NO bond, what we can say in the trend is the thermal stability. How stable is it to heat? The thermal stability of the nitrates will increase. It become more stable to heat. So of the group 2 nitrate, M2 plus NO3 minus, so it's MNO3 twice, it will increases. Sometimes the question can change to temperature of decomposition. So the temperature required to decompose it will be much higher. Sometimes they can talk about the ease of decomposition. So it becomes much more difficult to decompose. So the ease of decomposition would decrease. Just playing around with words based on this last sentence here about the trend there. So I already described the trend, but I explained first and I described the trend because I find it easier. But whatever you do, doesn't matter the order, you still have to address both parts of the question for that full 3 marks there. What do we have in the next? We have the question, lithium nitrate. So you decompose lithium nitrate, you get a brown gas. The fact you get a brown gas, that means you get NO2 gas there. So very similar to what happens with group 2 nitrate, because what happened with group 2 nitrate when you decompose that, you will get the group 2 oxide, M2 plus or 2 minus, that is your solid group 2 oxide. You will get 2 NO2 gas, which is brown in color. You would also get a colorless gas, which you don't see, of course, because it's colorless gas. So what do you see? You don't see it. You just test for the gas. When you see the brown gas, you also need to test for the oxygen gas if you're doing this in practical. The ratio matches because 2 nitrate, they give you 2 NO2, and then this is 1 oxygen, 4 oxygen, 5 oxygen. You have 6 oxygen on the left. You just need 1 oxygen atom. But oxygen exists as a diatomic molecule. You must have half of it. Some teachers would say, write down 2, 2, 4, and 1 is perfectly the same equation, just divided by 2 there. Here, we don't have a group 2 nitrate. Instead, what we have here is the decomposition of lithium nitrate. And it says it follow similar kind of chemistry. This is Li plus because group 1 metal ion, NO3 minus. You're going to get lithium oxide, Li plus or 2 minus. So you're going to get 2 of that Li plus to balance out the charges of O2 minus to get the formula there. You will get a brown gas, which is NO2. And it's similar to that happens when you heat up magnesium nitrate, but it does not occur with other group 1 nitrate. So I'm going to assume that it also gives oxygen gas. And let me see if I balance the equation. 2 lithium there, so 2 of that nitrate. 2 NO3 will give me 2 NO2. And now what I have is 1 oxygen and 4 oxygen. So there's 5 oxygen. 2 times 3 is 6 oxygen. So again, I have this issue here where I cannot change the formula of the molecule, but I can change the number in front so that I have 1 extra oxygen, 1 oxygen atom, 4 oxygen atom, another 1 oxygen atom, altogether 6 oxygen atoms. 3 times 2, 6 oxygen atoms there. Very last bit of this question. Suggest why the group 1 nitrates other than LiNO3 do not decompose in this way. Do not decompose in this way. Well, what is so special about lithium? If you look at lithium and then you have that staircase relationship, so I think that this relationship is no longer that relevant in the new syllabus, but it used to be stated that you need to know something called the diagonal relationship. So it's the same thing when you have boron and silicon. So boron and silicon have similar kind of chemistry, and then you have aluminium just below boron, and then what we say is beryllium and aluminium. Beryllium and aluminium has similar kind of chemistry. So I'll give you an example. Al2O3 is amphoteric oxide. Now, all of the group 2 oxides are basic except for beryllium oxide, which is amphoteric. And why is that? There is such a thing called diagonal relationship. And where is the origin? What is the origin of this diagonal relationship? Well, like I said, it's no longer that relevant in your new syllabus, but then this diagonal relationship arises as a result of very similar electronegativity. Actually, it might still be asked in your new syllabus. If you look at AS Chemistry, if you look at the new syllabus, AS Chemistry, they can give you electronegativity values. This is stated in the 2022 syllabus, where they are expected to be able to use electronegativity values, and if they have similar electronegativity values, when they combine with oxygen, their property is going to be similar. So I stand corrected. I think it could be asked in the new syllabus as well. So we can say that because of the diagonal relationship, so that means only lithium has similar electronegativity. Do I want to say this? Only lithium has a similar electronegativity as magnesium. Therefore, lithium nitrate follows, not just lithium nitrate actually, lithium chemistry, lithium plus chemistry in general shows similarity or resembles to that of magnesium, the group 2 metal, to that of Mg2 plus metal there. Okay, so hopefully that makes sense there, but of course this is not for the group 1 metal, this is for group 2 nitrate there, group 2 metal nitrate decomposition in the presence of heat. Not too much you can write for that 1 marks, but it's definitely to do with diagonal relationship and similar electronegativity, therefore similar chemical reactivity as well. And that's the end of that 7 mark question there. In this next question, we have silver sulfate. This is about a sparingly soluble salt. So clearly speaking, they are going to ask you about KSP, which is equilibrium constant for a sparingly soluble salt. And they want you to state the units for 1 free, well actually it's not 1 free mark, it's just 1 mark. So pretty stingy here, this old paper. In the new paper, perhaps you get 1 mark for this and 1 mark for the unit. Anyway, so what you do first, you want to try and write an equation. So the solid dissolve in water, dissolve in solution to give you the ions. We get a silver plus aqueous ions and a sulfate aqueous ion. Every equation you write has to be balanced. So what we have there must be 2 Ag plus. Hang on, just give me a minute. Don't know why this thing doesn't move properly. So 2 Ag plus because I have 2 Ag plus there. 1 of the sulfate give you 1 of the sulfate. They want the KSP expression. So what I don't want to do is, I don't want to write that as the KSP expression. We should write the proper answer in here. So what we get is, we have, what we have there will be concentration. Actually, there's no divide by anything because this is a solid on the right hand side. So we just have the, what I mean is you have a solid on the left hand side. So you're just going to write in the concentration of the aqueous ions on the right hand side. So 2 of that Ag plus, and therefore you raise the power in the stoichiometric equation for the concentration there in the KSP equation. So just like you would do for Kc expression as well as Kp expression back in AS chemistry. Here we have a concentration square and we have another concentration. So we're going to get a total of mole per dm cube square multiplied by mole per dm cube. You're going to get mole to the power of 3. And then dm minus 3 square is dm minus 6. And then you add it with minus 3. So minus 6 plus minus 3 is going to be minus 9. So you get that mole cube, dn minus 9, bookkeeping there. Based on this KSP equation there, so I can move my equation down there because I'm going to do some sort of equilibrium question now. Calculate the value for this KSP. So if you want the KSP expression, you need the concentration of Ag plus. And we have the concentration of its saturated solution. So this is like Ag2SO4 saturated solution. This is as much of it dissolved in water as possible. So if I have 1 mole of this that dissociate, it will give me 2 mole and 1 mole of that. So I only have 2.5 times 10 to the minus 2 that dissociate in there. So if that is 2.5 times 10 to the minus 2 mole per dm cube, so therefore, this thing is this one, So 1 mole of this gives 2 mole of that. If this much dissolve in water in the saturated solution, therefore the concentration of Ag plus is going to be 2 times 2.5 times 10 to the minus 2. I get 5.0 times 10 to the minus 2 mole per dm cube. Now this one 1 mole of these give you 1 mole of the sulfate. So the concentration of the sulfate is still 2.5 times 10 to the minus 2 mole per dm cube. They want us to calculate the value. So the KSP is just going to be put in the value carefully and use bracket. This is square for the concentration of the Ag plus, and this is multiplied by the 2.5 times 10 to the power minus 2. So key that into your calculator carefully. So 5 times 10 to the minus 2. So you will write in 5.0 and then exp minus 2 on your calculator, and you square that. You multiply by 2.5 times 10 to the minus 2, and altogether you get 6.25 times 10 to the power minus 5. Of course, you have the unit there previously, so I don't have to write it again. But in my final answer, I should always try to be as accurate as possible by including the unit that I did correctly from the previous part of the question there. What do they want here? They want to relate solubility to the lattice, the enthalpy change of solution, which is that thing there, as well as the enthalpy change of hydration. So if I have the solid there, the silver sulfate, the silver 1 sulfate, by the way, because it's very important to name with the Roman numeral for the oxidation number, because it's transition metal, they can have more than one oxidation number there. What is what? So they haven't labeled arrow there, but this is being formed from something. This is being formed from its gaseous ions. That is going to be lattice enthalpy or lattice energy. So I'm just going to write down the gaseous ion. Of course, you have 2 Ag plus, so I also have to balance my equation so that everything is correct there. I've done a mistake there. It shouldn't be aqueous. It has to be from its gaseous ions in order for you to define this as lattice correctly. So delta H, theta lattice, this is the lattice energy. Is the energy required? Well, actually not required. It's the enthalpy change. In fact, it's going to be exothermic, because it's enthalpy change when you form 1 mole of the ionic solid from its gaseous ions. Now, how about solution and hydration? So these are gaseous ions. In order to relate to hydration, what you will get is you will get hydration and blah, 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 blah. We don't have that thing there, so we just need to label hydration. But actually, this thing is 2 times the hydration of Ag plus. By right is 2 times the hydration of Ag plus, because you are hydrating 2 mole of this gaseous ion, whereas hydration is for hydrating 1 mole of gaseous ion, surrounding it or reacting it in a large amount of water, get an infinitely dilute solution there. And this one is plus 1 times the hydration of the sulfate. Now, why do I write this here? Because the question did not specify hydration of cations or hydration of anion. They just said enthalpy change of hydration. Using this as an example, complete it relating these 3. So based on the question, we are only given this value, this expression, not value. So I've just written down this expression, but I know this one here is represented by this whole thing there. Okay. And of course, the last thing, we have to write the arrow. The arrow is actually going downward, because hydration of the cation, hydration of the anions, you are going to get 2 Ag plus aqueous plus SO42 minus aqueous, like that. And this is the solid dissolving in a large amount of water to give you an infinitely dilute solution under standard conditions. That is going to be your enthalpy of solution there. Standard enthalpy change of solutions, because it's under standard conditions, 298 Kelvin, 1 atm pressure. If you see this Hess cycle, Hess law says that enthalpy change of a reaction is independent. It does not depend on the route you take, as long as you start from the same reactant and end up at the same product. So if I think about, I don't know, it doesn't matter which way around I think actually. If I just start from there, this direct route, so enthalpy of solution, there's the direct route. This is the indirect route. I'm going opposite, so it's going to be minus the lattice. And then I'm going the same way, so it's plus the hydration, which include the hydration of the cation as well as the hydration of the anion, as I have written down above. But since the question just said enthalpy of hydration in there, so I'm just going to put the enthalpy of hydration in there, and that's the 4 marks there in that question. Next, we have this question. We have some electrochemistry. So on the right hand side, you will see you use a silver metal. So this is silver metal, the metal itself as the electrode. And why do we do that? Because we have Ag2SO4 aqueous, and this is not very soluble, obviously. It's by saturated solution, so you get Ag2SO4. So this thing there, not very soluble. This is a bad electrolyte, because how are you going to get 1 mole per dm cube, 1.00 mole per dm cube? It's going to be almost impossible, especially when this thing is very sparingly soluble. That's why you did KSP just now, almost not soluble at all. On this side, you have platinum electrode, and you have a system where you have iron 3. So this is actually iron 3, because you have iron in the 3 plus oxidation number. It's iron 3 sulfate there. And then this bottom one is actually iron 2, because it's iron 2 plus, and then sulfate. So iron 3 versus iron 2. This is metal ion, and metal ion, as stated in the syllabus, you must use a platinum, which is an inert electrode, as you have a 1.00 mole per dm cube equimolar mixture of 1.00 mole per dm cube iron 3 plus, and also 1.00 mole per dm cube of iron 2 plus. Now we gotta use the data booklet. Of course, in the real 2022 exam onwards, the data booklet will be provided inside the question paper itself. So make sure you will choose the right one. This is the iron 3 plus, iron 2 plus redox system. For this system on the left hand side, it's metal ion and metal ions. So 3 plus going to 2 plus, this is plus 0.77 volt. And the other one there will be E naught Ag plus Ag. So alphabetical order, Ag should be easy to find. The first one there, so plus 0.80 volt. So looking at that, I should be able to see that this one is the more positive E naught compared to the iron 3, iron 2 system. So what can I do here? Let me see if I can move it around a little bit more. So 1, 2. Then what do I do next? I just need to find E cell. So E cell is going to be the E red minus the E ox. The more positive value is going to be the silver system. So that is plus 0.80 minus plus 0.77. What you're going to get is something positive, because the more positive value favors reduction, and the less positive value favor oxidation. So I get that as plus 0.03 volt. Calculator will not show you the plus, but E cell, as stated in all the E naught values, sign, value, and unit, unless you're 0.00, which is not likely unless you have the standard hydrogen electrode. They are looking now for the positive electrode. If we think about the positive electrode, electrons come here. Electrons go to positive electrode. Be very careful. We are not doing electrolysis. We are doing a electrochemical cell system. So electrons are negatively charged. Electrons will flow towards the positive electrode. Now, which one is the E red? The E red is the more positive one. So this is E red. E red is where you gain electrons. You gain electrons at the E red. So electrons go to the E red. The E red is the Ag plus and Ag. So electrons go here. Electrons go here because it is reduction here. It's the E red. And if electrons come here, electrons are negatively charged. This makes the silver electrode as the positive electrode. So the answer there must be silver electrode, because electrons come here and you lose the electrons from the iron 2, iron 3 system here. Okay. Now that was based on the E naught cell value. That was based on the value in the data booklet, assuming standard concentration. But this question now is asking you, how would the actual E cell vary, okay, compared to the E cell under standard condition? Explain your answer for just 1 mark. We can see that in this equilibrium, this thing is not going to be under standard conditions, as this is sparingly soluble. So the Ag2, don't know why that is not writing properly. So the Ag2SO4 is very sparingly soluble. So if it's only very sparingly soluble, so not very soluble at all in water, its concentration, so Ag plus concentration, falls way below, well below the standard conditions, well below the standard 1.00 mole per dm cube concentration. And if that is true, then what will happen to your reduction potential? Because you have Ag plus electrons going to Ag there, and this is your E naught of plus 0.80 volt. And remember, that was your E rate. That was what we said to be the E rate. So if you are way below 1.00 mole per dm cube, this equilibrium will favor to the left hand side. To try and increase the concentration of Ag plus, this equilibrium will favor to the left hand side. And when you favor the left hand side, when you shift to the left hand side, this will become less positive. Because you favor to the left hand side, then the E rate, which is the Ag plus and Ag, would be less positive. So if the E rate become less positive, as if this is not very close to zero now, if this thing become less positive, that means this is going to become less positive, this is going to become more negative or less positive, meaning the whole reaction is going to become less feasible. So day one on the E cell, I've only talked about E rate, so therefore the E cell, which is no longer standard, so no longer standard because you fall below the standard concentration, that will become less positive. So less positive, or you can say more negative. It's really up to interpretation there. Both will be acceptable and both will be correct as well. Okay. Now the next bit of this question, how would the E cell change if you add a little bit of concentrated Na2SO4? What does the Na2SO4 actually do? Let me just work out what is happening here. Something is wrong with my pencil actually. How would the E cell change if you add a little bit of concentrated sodium sulfate? We know that all sodium salts are soluble. If all sodium salts are soluble, we are going to get an increase in the sulfate concentration, because this is a common ion with this KSP equilibrium. Since we get more SO4 minus in the equilibrium, you can imagine the KSP equilibrium set up earlier in the question. If we have more SO4 minus from the sodium sulfate, this equilibrium will try to remove the SO4 minus from the equilibrium. It will shift to the left hand side. When you shift to the left hand side, you will get even lesser Ag plus concentration. You get even lesser Ag plus concentration as a result of this common ion there. They are just asking for how it would change. They don't ask for explanation. Actually, they do they? Actually, they might later on, but anyway. So when that happened, we get the common ion effect. And what is the common ion effect? It basically means that more Ag2SO4 precipitate out. And if that precipitate out more, your Ag plus aqueous is going to decrease. And when your Ag plus aqueous concentration decreases, this equilibrium for the Ag plus Ag is going to favor to the left even more. This is going to drop lower than 0.80. It's going to become less positive than 0.80. So how would the E cell change? Well, the thing that contains the Ag2SO4, how would the E cell change? If I add it to the Ag2SO4 there, the E cell would behave the same as here just now, because here my Ag plus concentration drops. Here my Ag plus concentration drops, so this equilibrium will shift to the left. This will become less positive, so the E rate become less positive. Less positive minus the same value, your E cell will become less positive. So E cell becomes less positive, or if you want, you can say more negative. That would be okay as well. Alright, so how about if I add it onto the other one, Fe3 plus and Fe2 plus? The sodium salt is soluble, so the iron 3 and the iron 2 are completely soluble. That's why here you have aqueous solution and aqueous solution. So adding sodium sulfate there is not going to change anything. It's not going to precipitate them out because they are not in equilibrium. They are completely soluble. So there should be no effect on the concentration of the iron 2 and iron 3 at all, as these are solution and these are not KSP equilibrium. So no effect on the E cell, because there will be no effect on the E ox whatsoever, because these things are already soluble. Okay, now explain any changes you have stated. They just want the any changes. We don't need to talk about the no effect. We need to talk about this thing here. So we can talk about the common ion effect. So Na2SO4 is a soluble salt. As the concentration of sulfate increases, what's going to happen is more Ag2SO4 precipitates out. And if more Ag2SO4 precipitate out, this is actually the common ion effect. It is not going to be relevant by you stating the effect without explaining it. It's not going to get you the marks. So more Ag2SO4 precipitate out, Ag plus concentration decreases. So the EOX, not the EOX, the E-red, which is for the Ag plus and Ag, just like how we explained for the previous bit of the question, this thing is going to shift to the left in order to try and increase the concentration of Ag plus. Lee-Chatelier principle, counteract the change to try and increase the concentration of Ag plus, shift to the left, this one become less positive. So if the E-red Ag plus Ag becomes less positive, so what will happen to the E cell then? The E cell will become less positive. Okay, so hopefully that makes sense to you. They're pretty stingy back then with just 1 mark for this long explanation here. Okay, the new syllabus, however, will probably ask you in terms of Nernst equation. So be aware that there is something called Nernst equation, which is to do with calculation of the electrode potential, of the cell potential, when you are no longer under standard conditions. So non-standard conditions, what is going to be your E cell, your cell potential there? That is part of the new syllabus from 2016 onwards. What do we have in this next question? This is the last bit of this long question. We are having a weak acid. So we have equilibrium there, weak acid. We are given some Ka value there. So we know that for a weak acid, Ka is H plus, and then the conjugate base over the Hx. These are all concentration at equilibrium. We also know that these are 1-to-1 ratio, the conjugate base and the weak acid H plus. So this is going to be approximated. You can approximate that to H plus square, and then you can approximate the bottom to the initial concentration of the acid, since very little of it dissociate when you are a weak acid. So what we have there really is we want the pH. So I can work out H plus is going to be the square root of Ka multiplied by Hx initial there. So subbing in the value, so 8.9 times 10 to the minus 4 times the initial concentration, which is 0.1 mole per dm cube. Don't forget to square root your final answer. So when I square root my final answer, I get 9.43398 times 10 to the minus 3. But what do I want? I want pH. pH is minus log 10 of H plus. So from my previous answer, I take the log 10 and then take the negative log 10 of it. I get 2.025. Looking at the value here, this is one significant figure, 0.1 mole per dm cube. Looking at the Ka, this is 1 and 2 significant figure. I would probably give these to 2 significant figure just to be appropriate with the data given in the question for this calculation. That's the end of this 13-mark question there. In this question number 5, we have atoms and ions, and we are talking about 3 subatomic particles, protons, electrons, and neutrons. And if we have this number on top, that is called the mass number. That is also known as the nucleon number. It's to do with the number of protons plus the number of neutrons, protons and neutrons in the nucleus of an atom. So carbon has 6 protons. That is the proton or the atomic number. So what we have there will be 6 protons. We have a 2 minus charge there. So that's because we have gained 2 electrons. There's 8 electrons. We have 14 minus 6, which is 8 neutrons there for this isotope of carbon 14 there. In terms of this next part of the questions, I don't think you need to relate, you need to learn about them. They are from the old syllabus prior to 2016. This was the group 14 chemistry that they would have learned previously. But the CCl4 is basically inert to hydrolysis, as the CCl bond is the longest out of the three. It's the shortest out of the three actually, because of the small size of carbons. So if it is the shortest, something is definitely wrong with this thing here today. It's the shortest bond out of CCl versus GeCl versus the SnCl, and therefore it is the strongest bond, and therefore not easily hydrolyzed, not easily broken or hydrolyzed. Okay, but as for the rest of it, I don't think we need to talk too much about that. That was basically the reason for the reactivity. This is in the AS bonding 2022 syllabus, where they will expect you to relate bond energy, covalent bond strength with bond length. This is to do with the size of your atom, and then you can relate to reactivity. If you need to break the bond, are you breaking a stronger bond or are you breaking a weaker bond? All right. As for this chemistry, this is actually quite a useful A2 electrochemistry question. So what you need to do is, we need to know that Cl2 is an oxidizing agent. So that's straight from your AS chemistry of halogens. So when that is true, if we look at the E0 value from the data booklet, so what does the CO2 give me? CO2 plus 2 electrons, that one is plus 1.36 volt. Should probably write better then, plus 1.36 volt. And then you are trying to use this as an oxidizing agent, so you're oxidizing the Sn2 plus to Sn4 plus. So we're looking at the Sn4 plus on the left hand side, because everything in the data booklet, the E0 value shows you reduction potential. So we have E0. Okay, I gotta fix this thing now. Okay, E0, Sn4 plus and Sn2 plus, and that give me plus 0.15 volt, whereas the E0 Pb4 plus and Pb2 plus, that give me plus 1.69 volt. So we are saying that there is a reaction between Sn2 plus and Cl2. So if we have a reaction between Sn2 plus and Cl2, what we're gonna get will be the Cl minus and the Sn4 plus. So Sn4 plus there, so 2 Cl minus, that will lose 2 electrons, and this will lose 2 electrons, and this will gain the 2 electrons. So this is the balance equation, and what you have there is your E cell, which is your E red minus your E ox. And if that is true, the Cl2 goes to Cl minus. This is going to be your E red, and this is going to be your E ox. So you can see that something which is more positive minus something which is less positive, you're going to get something positive. 1.36 minus 0.15. Your calculator show you 1.21, but you need to know electrochemistry must have sign, must have value, and must have unit. And you can relate this to the new syllabus. The new syllabus say delta G equal to minus NF E cell. And if the E cell is greater than 0, so the delta G is going to be lesser than 0. So what we can say is spontaneous and also feasible reactions related to delta G there. But an aqueous solution of PbCl2 does not react. So now we are onto the negative bit now. So if we react, if Cl2 oxidizes Pb2 plus to Pb4 plus, we need to show the E cell is going to be the E red, which is the Cl2 acting as oxidizing agent, so they will undergo reduction. So the E red is plus 1.36 from the chlorine, and then that is minus plus 1.69. As you could see, something smaller minus something bigger, that is going to be negative, and your calculator will show you something negative. So your delta G there, which is minus NF E cell. So N is the number of electron transfer, which is 2 electrons. F is a positive Faraday constant. Minus and the minus will give you positive. So delta G would be greater than 0. This is not feasible, not spontaneous. Answer the first bit, answer the second bit, write an equation for this reaction, which we already did, and that's the end of that 3 marks. Kind of a good electrochemistry question, although it's more related to all the syllabus on the group 14 chemistry there. Now this next bit of the question is definitely just electrochemistry, so this will be relevant to the current syllabus as well. What is the relationship? You just need to state it. So this is F equal to the Avogadro constant multiplied by the electronic charge, which is the charge for one electron. Faraday constant has a unit of 96,500 is the value. The unit is coulomb per mole. This is the charge. Is the charge for 1 mole of electrons. It's a charge for 1 mole of electrons. If you have the charge for 1 electrons, you multiply by 1 mole of electron, you're going to get the charge for 1 mole of electron. That's basically what it means there. Now, when you pass a current of 1.2 ampere and you pass it over 30 minutes into dilute sulfuric acid, we are going to do an electrolysis of dilute sulfuric acid straight from your O level or IGCSE level chemistry. You have the sulfuric acid which give you H plus, SO4 2 minus, H plus and OH minus. So the H plus is just going to, dissociate one of them. And when I say dissociate, what I mean is discharge. Discharge at the cathode, that's the right word. Between the hydroxide and the sulfate is the hydroxide that's going to get discharged. So the H plus the 2 electrons that will go to the H2. This will happen at the cathode. Reduction happen at cathode for your electrolysis. As for your OH minus, the OH minus will become O2 and H2O and electrons, and you balance the equation with 4 OH minus and 2 H2O and 4 electrons there. So that is your oxidation at the anode there. Oxidation at the anode because reduction happened at the cathode. Overall, what you're gonna get is you're gonna get the H2O getting electrolyzed, the H2O getting electrolyzed to give you hydrogen at the cathode and oxygen at the anode there. And you're going to have H2SO4 remaining, and in fact they're going to become more and more concentrated as these electrolysis continue there. So what do we get? Blah blah blah. This is the reaction that happens at the anode because this is oxidation. So this is an alternative equation which you can write. It's pretty much the same thing as that. It's just the water dissociating in solution to give you the O2 and the water there. And the OH minus come from the water. So essentially you're still losing electrons there, and you will still get the completely balanced equations even if you write this, or this will be pretty much the same there. But what do they want here? They want you to calculate a value for Avogadro constant. They're trying to guide you. There are 5 things to be calculated there, and there are 4 marks to run up these 15 marks questions. So let's try to do them one by one. First of all, calculate the number of mole of oxygen produced. So let me just number these stuff that they want us to calculate. So number 1, the number of moles of oxygen produced. Oxygen is a gas, and I get 130 cm cube there. So this is the gas volume, and this has to be divided by 24,000. Oh, this is frustrating. Something is definitely wrong with this thing here. So 130 divided by 24,000, and this is cm cube, and this is cm cube per mole. We know that in the periodic table at the bottom, it's given as 24.0 dn cube per mole. Here's 24,000 cm cube per mole because it's in cm cube there. So we want to calculate it, so we want to give a value. So, calculate and put it into a calculator. 130 divided by 24,000. I get 5.417 times 10 to the minus 3 mole. I don't want to run up too early, so I just leave it as 4 significant figure for the time being. That should be enough. Now, what is the number of mole of electrons? Well, from the equation, 4 mole of electrons react with, is produced along with 1 mole of oxygen. So I will relate the mole of electrons to the oxygen. 4 mole of electrons, 4 mole of electrons is to 1 mole of oxygen, is to 1 mole of oxygen. So what is my actual mole of electrons? Is to the 5.17 times 10 to the minus 3 mole of the oxygen. So students who are used to my channel, you know that this is the usual method I like to use when I talk about This is really frustrating actually. When I talk about my mole ratio, so actual number of mole of electrons is going to be 4 times that answer from the previous bit. 5.417, 5.41, I can't even press my calculator correctly, times 10 to the minus 3 times 4, so this one will give you 0.021668 mole. 21668 mole, okay, never mind. So now I need to find the number of coulomb pass. This depends on the question. So you pass 1.2 amperes over 30 minutes. So we know Q equal to IT, I there, and then the T is to be in seconds. So it's 1.2 times 30 times 60. So Q is equal to IT. That was 1.2 amperes. And multiplied by 30 minutes, converted into 60 seconds. Well, converted into seconds by multiplying by 60. So 1.2 times 30 times 60, I get 2160 coulomb. So this much mole of electrons is for 2160 coulomb altogether. What's the next thing that they want? The number of electrons pass. The number of electron pass. If you look at the data booklet, of course, you'll be given this data in the question for the new syllabus, obviously. So we know that this charge, 2160 coulomb, is for 0.021668 mole of electrons. What are we trying to find actually? We want to find the number of electrons, that are passed. We know that the charge of one electron stated in the data booklet will be 1.60 times 10 to the minus 19 coulomb. So I guess if that is for that, we want to find the mole of electrons, right? We want to find the mole of electrons. So what do we want? We want the number of electrons passed. This is for one electron, and we have this much charge. This is for one electrons. I think I've gotten this the other way around. So, 2160. Nope, that doesn't make sense. 1.60 times 10 to the minus 19 coulomb is for one electron. So 2160 coulomb is for how many electrons? Yeah, that seems to be the right way around. For direct proportion. So you have greater number of charge. That means you must have greater number of electrons like that. So 2160 divided by 1.6 times 10 to the minus 19, I get 1.35 times 10 to the 22 electrons. This is the number of electrons. Last but not least, what do I need to do? I need to get the number of electrons in 1 mole of electrons. So we know that this is the mole of electrons, and this is the number of electrons. So the relationship between Avogadro constant and this actual mole of electrons is going to be the charge for 1 mole of electrons. What am I doing actually? We want the number of electrons passed, so we did. We want the number of electrons in 1 mole of electrons. The number of electrons in 1 mole of electrons. So the number of electrons is equal to Avogadro's number multiplied by the mole of electrons. If we want the Avogadro's constant, now what do they want? They want the number of electrons passed. That one should be okay. The number of electrons passed. The number of electrons in 1 mole. The number of electrons in 1 mole is Avogadro constant. So that is the number of electrons divided by the mole of electrons. That is the number of electrons, which is 1.35 times 10 to the 22, divided by the number of mole of electron from the previous bit of the question earlier. And this should give you your Avogadro constant divided by that. And I get 6.23 times 10 to the 23. And this is to 3 significant figure. It is the number of electrons in 1 mole of electrons. Okay, so that's the end of that 4-mark question, and that concludes that 15 marks question overall. In this question number 5, we have atoms and ions, and we are talking about 3 subatomic particles. protons, electrons, and neutrons. And if we have this number on top, that is called the mass number. That is also known as the nucleon number. It's to do with the number of protons plus the number of neutrons, protons and neutrons in the nucleus of an atom. So carbon has six protons. That is the proton or the atomic number. So what we have there will be 6 protons. We have a 2 minus charge there. So that's because we have gained 2 electrons. There's 8 electrons. We have 14 minus 6, which is 8 neutrons there for this isotope of carbon 14 there. In terms of this next part of the questions, I don't think you need to you need to learn about them. They are from the old syllabus prior to 2016. This was the group 14 chemistry that they would have learned previously. But the CCl4 is basically inert to hydrolysis as the CCl bond is the longest out of the 3. It's the shortest out of the 3 actually, because of the small size of carbon. So if it is the shortest, something is definitely wrong with this thing here today. It's the shortest bond out of CCl versus GeCl versus the SnCl, and therefore it is the strongest bond, and therefore not easily hydrolyzed, not easily broken or hydrolyzed. Okay, but as for the rest of it, I don't think we need to talk too much about that. That was basically the reason for the reactivity. This is in the AS bonding 2022 syllabus, where they will expect you to relate bond energy, covalent bond strength with bond length. This is to do with the size of your atom, and then you can relate to reactivity. If you need to break the bond, are you breaking a stronger bond or are you breaking a weaker bond? All right. As for this chemistry, this is actually quite a useful A2 electrochemistry question. So what you need to do is, we need to know that Cl2 is an oxidizing agent. So that's straight from your AS chemistry of halogens. So when that is true, if we look at the E0 value from the data booklet, so what does the Cl2 give me? Cl2 plus 2 electrons, that one is plus 1.36 volt. Should probably write better then, plus 1.36 volt. And then you are trying to use this as an oxidizing agent, so you're oxidizing the Sn2 plus to Sn4 plus. So we're looking at the Sn4 plus on the left hand side, because everything in the data booklet, the E0 value shows you reduction potential. So we have E0. Okay, I gotta fix this thing now. Okay, E0, Sn4 plus and Sn2 plus, and that give me plus 0.15 volt, whereas the E0 Pb4 plus and Pb2 plus, that give me plus 1.69 volt. So we are saying that there is a reaction between Sn2 plus and Cl2. So if we have a reaction between Sn2 plus and Cl2, what we're gonna get will be the Cl minus and the Sn4 plus. So Sn4 plus there, so 2 Cl minus, that will lose 2 electrons, and this will lose 2 electrons, and this will gain the 2 electrons. So this is the balance equation, and what you have there is your E cell, which is your E red minus your E ox. And if that is true, the Cl2 goes to Cl minus. This is going to be your E red, and this is going to be your E ox. So you can see that something which is more positive minus something which is less positive, you're going to get something positive. 1.36 minus 0.15. Your calculator show you 1.21, but you need to know electrochemistry must have sign, must have value, and must have unit. And you can relate this to the new syllabus. The new syllabus say delta G equal to minus NF E cell. And if the E cell is greater than 0, so the delta G is going to be lesser than 0. So what we can say is spontaneous and also feasible reactions related to delta G there. But an aqueous solution of PbCl2 does not react. So now we are onto the negative bit now. So if we react, if Cl2 oxidizes Pb2 plus to Pb4 plus, we need to show the E cell is going to be the E red, which is the Cl2 acting as oxidizing agent, so they will undergo reduction. So the E red is plus 1.36 from the chlorine, and then that is minus plus 1.69. As you could see, something smaller minus something bigger, that is going to be negative, and your calculator will show you something negative. So your delta G there, which is minus NF E cell. So N is the number of electron transfer, which is 2 electrons. F is a positive Faraday constant. Minus and the minus will give you positive. So delta G will be greater than 0. This is not feasible, not spontaneous. Answer the first bit, answer the second bit, write an equation for this reaction, which we already did, and that's the end of that 3 marks. Kind of a good electrochemistry question, although it's more related to all the syllabus on the group 14 chemistry there. Now this next bit of the question is definitely just electrochemistry, so this will be relevant to the current syllabus as well. What is the relationship? You just need to state it. So this is F equal to the Avogadro constant multiplied by the electronic charge, which is the charge for 1 electron. Faraday constant has a unit of 96,500 is the value. The unit is coulomb per mole. This is the charge. Is the charge for 1 mole of electrons. It's a charge for 1 mole of electrons. If you have the charge for 1 electrons, you multiply by 1 mole of electron, you're going to get the charge for 1 mole of electron. That's basically what it means there. Now when you pass a current of 1.2 ampere and you pass it over 30 minutes into dilute sulfuric acid, we are going to do an electrolysis of dilute sulfuric acid straight from your O level or IGCSE level chemistry. You have the sulfuric acid, which give you H plus, SO4 2 minus, H plus and OH minus. So the H plus is just going to, dissociate one of them. And when I say dissociate, what I mean is discharge. Discharge at the cathode, that's the right word. Between the hydroxide and the sulfate is the hydroxide that's going to get discharged. So the H plus the 2 electrons that will go to the H2. This will happen at the cathode. Reduction happen at cathode for your electrolysis. As for your OH minus, the OH minus will become O2 and H2O and electrons, and you balance the equation with 4 OH minus and 2 H2O and 4 electrons there. So that is your oxidation at the anode there. Oxidation at the anode because reduction happened at the cathode. Overall, what you're going to get is you're going to get the H2O getting electrolyzed, the H2O getting electrolyzed to give you hydrogen at the cathode and oxygen at the anode there. And you're going to have H2SO4 remaining, and in fact they're going to become more and more concentrated as these electrolysis continue there. So what do we get? Blah blah blah. This is the reaction that happens at the anode because this is oxidation. So this is an alternative equation which you can write. It's pretty much the same thing as that. It's just the water dissociating in solution to give you the O2 and the water there. And the OH minus come from the water. So essentially you're still losing electrons there, and you will still get the completely balanced equations even if you write this, or this will be pretty much the same there. But what do they want here? They want you to calculate a value for Avogadro constant. They're trying to guide you. There are 5 things to be calculated there, and there are 4 marks to run up these 15 marks questions. So let's try to do them one by one. First of all, calculate the number of mole of oxygen produced. So let me just number these stuff that they want us to calculate. So number 1, the number of moles of oxygen produced. Oxygen is a gas, and I get 130 cm cube there. So this is the gas volume, and this has to be divided by 24,000. Oh, this is frustrating. Something is definitely wrong with this thing here. So 130 divided by 24,000, and this is cm cube, and this is cm cube per mole. We know that in the periodic table at the bottom, it's given as 24.0 dm cube per mole. Here's 24,000 cm cube per mole because it's in cm cube there. So we want to calculate it, so we want to give a value. So calculate and put it into a calculator. 130 divided by 24,000, I get 5.417 times 10 to the minus 3 mole. I don't want to round up too early, so I just leave it as 4 significant figure for the time being. That should be enough. Now, what is the number of mole of electrons? Well, from the equation, 4 mole of electrons react with, well, is produced along with 1 mole of oxygen. So I will relate the mole of electrons to the oxygen. 4 mole of electrons, 4 mole of electrons is to 1 mole of oxygen, is to 1 mole of oxygen. So what is my actual mole of electrons? Is to the 5.17 times 10 to the minus 3 mole of the oxygen. So students who are used to my channel, you know that this is the usual method I like to use when I talk about, this is really frustrating actually, when I talk about my mole ratio. So actual number of mole of electrons is going to be 4 times that answer from the previous bit. 5.417, 5.41, I can't even press my calculator correctly, times 10 to the minus 3 times 4, so this one will give you 0.021668 mole. 21668 mole, okay, never mind. So now I need to find the number of coulomb pass. This depends on the question. So you pass 1.2 amperes over 30 minutes. So we know Q equal to IT, I there, and then the T has to be in seconds. So it's 1.2 times 30 times 60. So Q is equal to IT. That was 1.2 amperes. And multiplied by 30 minutes, converted into 60 seconds. Well, converted into seconds by multiplying by 60. So 1.2 times 30 times 60, I get 2160 coulomb. So this much mole of electrons is for 2160 coulomb altogether. What's the next thing that they want? The number of electrons pass. The number of electron pass. If you look at the data booklet, of course, you'll be given this data in the question for the new syllabus, obviously. So we know that this charge, 2160 coulomb, is for 0.021668 mole of electrons. What are we trying to find actually? We want to find the number of electrons, that are passed. We know that the charge of one electron stated in the data booklet will be 1.60 times 10 to the minus 19 coulomb. So I guess if that is for that, we want to find the mole of electrons, right? We want to find the mole of electrons. So what do we want? We want the number of electrons passed. This is for one electron, and we have this much charge. This is for 1 electrons. I think I've gotten this the other way around. So, 2160. Nope, that doesn't make sense. 1.60 times 10 to the minus 19 coulomb is for 1 electron. So 2160 coulomb is for how many electrons? Yeah, that seems to be the right way around. For direct proportion. So you have greater number of charge. That means you must have greater number of electrons like that. So 2160 divided by 1.6 times 10 to the minus 19, I get 1.35 times 10 to the 22 electrons. This is the number of electrons. Last but not least, what do I need to do? I need to get the number of electrons in 1 mole of electrons. So we know that this is the mole of electrons, and this is the number of electrons. So the relationship between Avogadro constant and this actual mole of electrons is going to be the charge for 1 mole of electrons. What am I doing actually? We want the number of electrons passed, so we did. We want the number of electrons in 1 mole of electrons. The number of electrons in 1 mole of electrons. So the number of electrons is equal to Avogadro's number multiplied by the mole of electrons. If we want the Avogadro's constant, now what do they want? They want the number of electrons passed. That one should be okay. The number of electrons passed. The number of electrons in 1 mole. The number of electrons in 1 mole is Avogadro constant. So that is the number of electrons divided by the mole of electrons. That is the number of electrons, which is 1.35 times 10 to the 22, divided by the number of mole of electron from the previous bit of the question earlier. And this should give you your Avogadro constant divided by that. And I get 6.23 times 10 to the 23. And this is to 3 significant figure. It is the number of electrons in 1 mole of electrons. Okay, so that's the end of that 4-mark question. And that concludes that 15 marks question overall. In question 6, we have 1,3-dimethyl-benzene. So this is a 1,3-dimethyl-benzene. So 1, 2, 3. Because if you go the other way around, 1, 2, 3, 4, 5, that 1, 5 is going to be bigger than 1, 3. So 1, 3 is the correct name. What you have done is you have done a substitution here. So you have done a substitution. This is what you call the type of reaction, because this is as stated in the AS introductory chemistry, the terminology. The mechanism is going to be electrophilic substitution. In the current A2 syllabus, you will learn this as Friedel-Crafts alkylation. Friedel-Crafts alkylation is not the mechanism. It is not the type of reaction. It is the name for the specific reaction there. And then this next one is what you call Friedel-Crafts acylation. So that thing there is Friedel-Crafts acylation informing that acyl group there. You must have done a substitution again. Your type of reaction is substitution, but your mechanism is going to be electrophilic substitution on the benzene ring. We don't call it Friedel-Crafts acylation, even though this is the name stated in the syllabus, because it is not a mechanism. It's just the name of the reaction there. So the rest of it, you have done another electrophilic substitution there. So the very last step 3, the type there again is substitution, as you have substituted another 2 hydrogen on the benzene ring with NO2 and NO2. This mechanism is again electrophilic substitution, but in each of these electrophilic substitution, you have used a different electrophile in order to substitute onto the benzene ring. Here you have used an alkyl group. Here you have used an acyl group. Here you have used an NO2+. So let me just write that down. You have introduced a NO2+. You have introduced a COCH3, an acyl group. This is called an acyl group. And as for step 1, you have introduced a carbocation and alkyl group. This is alkylation. This is acylation. This is nitration, nitro group. Okay. Now, the only byproducts of step 2 is HCl. That is because you kick out the H+, and then you kick out the Cl- from the acyl chloride. So suggest the reagent that was used. It has to be CH3COCl. They are not asking for the formula. They are not asking for the name. You could have given the formula like that, or you could give the name, but the name has to be correct. It is a 2-carbon acyl chloride. The name is called ethanoyl chloride. If you choose to give the name, it has to be spelled properly. I would always go for the formula unless I have no choice. The next question suggests the type of reactions occurring in both step 2 and also step 3. They're looking for the type of reaction, not the name of reaction, but the type of reaction, which I've stated both of them are substitution reaction. That you have substituted the hydrogen of the benzene ring with an electrophile. This is an acyl group electrophile. This is a nitro group electrophile there. What is the reagents and condition needed for step 3? This is in your case study, obviously, nitration. So you need concentrated HNO3 and also concentrated H2SO4 in order to give you this electrophilic mixture that contain NO2+. And the conditions, well, you need to reflux these at very high temperature, around 50 to 60 degrees Celsius. Suggest the structures of the two products when A is reacted with alkaline aqueous iodine. Alkaline aqueous iodine is the classic iodoform test. So iodoform test will give you a yellow precipitate. This yellow precipitate is triiodomethane. You also know it as iodoform triiodomethane there. And where does this carbon come from? it comes from this methyl ketone. So it's a test for CH3CO or CH3CHOH. So this carbon has been chopped off, it's been fragmented from the original part of the molecule. So that's CH3CO carbonyl or CH3CHOH as part of alcohol chemistry. What do we have in A? We have this mass ketone there because we have this CH3CO. So what is being fragmented will be this bond here. So you know that thing there will be lost as CHI3. So what you will get then is you will oxidize the ketone essentially, and you will get a carboxylic acid. However, you are in basic condition because it has to be done in alkaline aqueous iodine. What you will get will be the carboxylate salt. So what I can do is, this is blah blah blah. So let me try and draw the product on this side, on the left hand side. Nothing wrong with the nitro group, so it will not react. Nothing wrong with the alkyl groups, they will not react. So what will react is this thing here. So the CH3CO, now you have O minus, and you are in alkaline aqueous conditions. They did not mention what is the base. It could be potassium hydroxide, it could be sodium hydroxide. We do not jump to conclusion, therefore I don't write the Na plus there. I just know that it's under basic condition, and under basic condition I will not get the acid product. Instead I will get the salt of the acid because this is under alkaline condition. We don't know whether it's Na plus or K plus. They never mention what alkali they use unless you assume. An assumption can be dangerous unless you know exactly what you're assuming there. Okay, triiodomethane, this is called the iodoform. This is the yellow precipitate. It comes from that CH3 group that has been fragmented from that methyl ketone. CH3CO get chopped off there, the ketone get oxidized somehow. Under these conditions you get a carboxylic acid that get deprotonated to give you the salt under alkaline condition, and that terminal carbon there become iodoform yellow precipitate. Some more chemistry here. So 1,3-dimethylbenzene, you can also use it as a starting material, and you react that to form dicarboxylic acid. So this was 1,3-dimethylbenzene, and now you get 1,3 is that 1,3? How do I name it? This one should be benzoic acid. I guess this is a dibenzoic acid. 1,3-dibenzoic acid. So a CO2H bonded to a benzene is called benzoic acid. I've got two CO2H on the benzene at position 1 and 3. This one on the other hand is called 1,3-diphenylamine because, you know, amine bonded to a benzene is called phenylamine. So what I get is diamine, but they are both phenylamine, so it's 1,3-diphenylamine. Now this going to this, the arrow matters, so focus on the arrow. So this is right going to left. So what happened is loss of oxygen, gain of nitrogen. Look at the hydrogen, look at the nitrogen atoms. It gains hydrogen, it loses the oxygen. This is very clearly step 2 is your classic reduction of your nitro group, which you can easily do with what's that thing there, reduction of nitro. You use SN and HCl aqueous and reflux, but this is in acidic condition, so the concentrated HCl actually, not aqueous HCl, I beg your pardon. So con HCl reflux with tin will reduce the nitro specifically to the phenylamine, but this is an acidic condition and it will protonate on the phenylamine, which is weakly basic. So what happened then is you have to add excess NaOH afterwards because you have to neutralize the H plus and return you back to the diphenylamine because they will not react further with NaOH. It will just take away the H plus that the phenylamine already protonated in order for you to give you this one here. This is an oxidation of the alkyl side chain on the benzene ring. So the alkyl side chain, so oxidation, very special oxidation of the alkyl side chain of benzene as stated in the syllabus, and you just do this with acidified KMnO4 and reflux. Not too sure if they're asking you for the conditions or not, but they are asking us to draw the structure of one repeat unit of this condensation polymer. In fact, that is the next question actually. What kind of polymer this is? You're going to form an amide. So straight from IGCSE or O-level chemistry, the very last few topics involve polymerization. So carboxylic acid and this NH2 will come together. They call it condensation. You will lose the H and you will lose the OH from the acid. You will lose the OH from the acid and the H from the amide. So what happened then is you will get something that looks like this. If I draw the carboxylic acid first, CO like this, the new bond that you form will be this one, the pink one. And this new bond is connected to the orbit of the molecule, the NH. And then this is bonded to something else. And then the other one is bonded to something else. They are not asking us to draw the repeat unit fully displayed. So I am not going to draw the repeat unit fully displayed, because sometimes they will say show the amide bond fully displayed. So you have to show the CO and H fully displayed, including the atom. But they didn't say that here, so I should be able to leave in the skeletal formula format like this. This is from the dicarboxylic acid. This is the new amide bond that you form. This is also another amide bond that you form, but this will already be bonded to the other carboxylic acid fragment on the other monomer. So there are two monomers, 1 and 2, and these two monomers, now give you this repeat unit, which consists of one fragment of this monomer and the other fragment of that monomer. You get amide bond formed as a result of condensation reaction. This is a condensation polymer. In this condensation reaction, two molecules come together and you kick out a small molecule, because in your syllabus, you will know that condensation is a two-step mechanism. Condensation is two-step. The first step is what you call nucleophilic addition from the AS chemistry, and then elimination of a small molecule, which is usually water. But then, you can eliminate H2O or HCl if you use things like acyl chloride instead of the carboxylic acid, because acyl chloride is far more reactive compared to carboxylic acid. Here you use carboxylic acid, and so you're not going to kick out HCl, you're going to kick out water. The carboxylic acid lose the OH, they combine with that H there, you will get water. I will just write down H2O as the formula there, because they didn't ask for the name, they just asked for what is the product. I could just give the formula there. What is the reagents and conditions for step 2? Step 2 was the reduction of the nitro group of benzene into phenylamine. In the old syllabus, they used to just stop there, but I am pretty sure in the 2022 syllabus, they are now far away that students know that this is basic group, and they will protonate if you just do it in con HCl, and as such you have to neutralize the excess HCl by using excess NaOH, so that you will take away the H plus from the phenylamine that will get protonated previously, and then only then you will get the free form of the acid, and only then you will get the free form of this diphenylamine there. So I'm just gonna copy paste that so that I don't have to write. Actually, I can write the whole thing. This is reduction of the nitro group of nitrobenzene. So as I did mention, we can start off by talking about tint and concentrated HCl. They also want the condition, so reflux that. Then very importantly, then you have to add excess NaOH so that you can neutralize all the concentrated HCl and give you back the phenylamine form. In this next question, suggest how and why the properties of the polymer might change if you replace some of the diamine with 1,3,5-triaminobenzene. If we replace some of the diamine monomer, so what's going to happen is you are going to get that NH, and now you're going to get CO. What's going to happen? What is going to happen? So that thing there, it looks like it's going to be bigger because it's going to extend in this direction. It's going to extend in this direction. It's going to extend in this other direction as well. It's going to extend in all three directions. Previously, it will just extend in two directions, here and here. So it will change the structure, I guess. How and why the properties might change. Well, we have extra NH2 group that can polymerize with the dicarboxylic acid in another direction. So what we can see here is that when they polymerize this way, we get a symmetrical structure, right? When we get a symmetrical structure, I wonder what I can say. I will get amide, and this thing are amides. So amides has lone pair on the nitrogen. Yes, they are not basic or acidic. They are neutral. Amides are neutral. And we know that amides can form hydrogen bond because you have hydrogen bonded to electronegative nitrogen. They can form hydrogen bonds among the layers of the polymers. So the fact that you are branching out with more of this polyamide group, because you can form more polyamide in the other direction, I can imagine that hydrogen bond will be stronger. So the properties will make it more soluble in water, I guess. Maybe. All right. Polymerize with dicarboxylic in another direction. More polyamide group or more amide group can form more hydrogen bonds, can form stronger hydrogen bond between themselves. And if they can form stronger hydrogen bonds, what can we say about properties? So perhaps you can say higher boiling point, perhaps higher solubility, perhaps. These are just suggestive kind of question, how and why. I'm just thinking about more of that polymer that extend the other direction. They can form hydrogen bond, more soluble in water due to hydrogen bond with water, higher boiling point because of stronger hydrogen bonds between different chains of the polymer, between different molecules of the polymeric chain. For that, just 1 mark to sum up these 10-mark questions on polymerization and some A2 organic chemistry there. In this question 7, we have some long chain alkanes. This is 4-methyl heptane. If you try to put number here, 1, 2, 3, 4, 5, 6, 7. How about if I go the other way? 1, 2, 3, 4, 5, 6, 7. It looks like it is symmetrical. So whether you go from left to right or right to left, this blue or pink color will put the branch group, which is 1 carbon methyl, CH3 there, at position 4 regardless. When we do cracking is defined as the breaking up long chain hydrocarbons into shorter chain hydrocarbons, which can be a mixture of alkane and alkenes, because these shorter chain hydrocarbons are more valuable, they are more in demand. So state the conditions, plural there, for cracking to happen. Usually the cracking we are referring to will be catalytic cracking. So when you think about catalytic cracking, we use things like Al2O3. You can use SiO2 as a catalyst. So Al2O3 or SiO2 as a catalyst. And you also need high temperature, but not as high as thermal cracking. This one can probably happen at, 500, 300 degrees Celsius, but definitely high enough temperature to force it to happen, as you do need to break covalent bonds. And that is just being helped. The rate of reaction is being made faster with the use of the catalyst, obviously. Okay. Suggest the structure of B. B is C3H8. It is still a hydrocarbon. We have just broken the 7-chain hydrocarbon into a 3-carbon hydrocarbon. I can be thinking about C3H8, CH3, CH2. Is that correct? CH3, CH2, CH3. Yeah, 3 plus 2 plus 3 is 8 hydrogen. It's entirely possible. It cannot be alkene because there are too many hydrogen there. It's CnH2n plus 2. The structure, they did not mention skeletal or display or structural. So, you can do skeletal, structural, or even display. You still get the 1 mark there. On to the next bit of the question. Compounds C, D, and E are isomers. They don't tell you what kind of isomers, whether it's structural or optical, you don't know. But they are C5H10. Most likely they are alkene, CnH2n. In fact, the next bit is chemistry of alkene. This is AS, and chemistry of alkene. This is to do with oxidation of alkene. And this is extreme condition. Concentrated acidified KMnO4 is going to be the extreme condition. And when you get the extreme condition for the oxidation of alkene, you're going to get the rupture of the carbon-carbon double bond. When we get CO2, that indicates you must have a CH2 double bond like this. This is what you call terminal. Terminal CH2 will give you carbon dioxide. Now you also get this compound F, which have 2 oxygens. There are 2 other possibilities you can have in a double bond. That was the first possibility. The second possibility is when you have RCH double bond, that will give you RCOH and a oxygen there. So you get a carboxylic acid from a RCH double bond. Continuing upwards, when you have RCR like that, so you have carbon of the double bond bonded to 2 other carbon. Here is carbon of the double bond bonded to 1 carbon and 1 hydrogen. So when you have 2 carbon there, what you're gonna get will be ketone. When you oxidize the alkene there, you're gonna get a ketone instead of a carboxylic acid. The very fact that we have 2 oxygen there would mean it cannot be a ketone with 1 oxygen. It has to be a carboxylic acid. So F must be carboxylic acid. F must be carboxylic acid. And if F is carboxylic acid, what does that tell us? That F comes from RCH double bond. F must come from RCH double bond like that. Now what is the next bit of the information? D and E are also alkene. They give a 1-to-1 mixture. 1-to-1 mixture of G and H. So G is 2 carbon carboxylic acid because again 2 carbon. And then H is also 2 carbon, cannot be ketone. So G and H must also come from RCH. So again, G, H, and also F, they come from RCH double bond. They give you carboxylic acid. Okay, which means G and H are carboxylic acid. So what do I know so far? G is probably the easiest one to think about because 2 carbon carboxylic acid, it must be ethanoic acid. A 2 carbon carboxylic acid, no other choices. They want to suggest structures. They did not mention display, skeletal or structural. My tag is always draw skeletal because it's fast, it's elegant, and you're expected to be able to do it. CH3, carbon from 4 bond. There's 1 there, 1, 2, 3. CH3, CO2H. The next thing is this 3 carbon carboxylic acid. So H must be propanoic acid. And H is 3 carbon carboxylic acid. You cannot isomerize 3 carbon acid because it's not long enough to branch out or anything. There can only be one answer there. If D and E are the alkenes, that give you G and H, and you get 1-to-1 mixture of each one of these from this alkene, that means D and E must be isomeric. D and E are most likely going to be cis and trans isomer. If I have RCH double bond, let me label this as like the pink one, and then this other one as like the black color one. So if I have the black color one, and then the pink color one, and then the pink color one, and the black color one like this. So I'm going to write in the carbon-carbon double bond. Okay, and then I would draw what happened on the other side. Now, if I have RCH double bond, so this is the carbon of the double bond, I must have RCH in order to give me carboxylic acid when I oxidize the alkene as chemistry. So that means I must have a CH3 on one side, carbon bond to carbon. The hydrogen is not bonded to carbon, so the carbon bonds to carbon, and I have a hydrogen on one side. This is 2 carbons bonded to the carbon in black, so I have a CH2, CH3, that is the CH2, CH3, RCH. When I break this double bond, RCH will give me a 1, 2, and 3 carboxylic acid, propanoic acid. This is the 2 carbon there, 1, 2, so RCH will give me a 2 carbon carboxylic acid, ethanoic acid upon oxidation under extreme condition. These 2 groups are on the same side of the carbon-carbon double bond. This is going to be your cis. This is going to be named 1, 2, 3, 4, 5. If you go the other way, you have 1, 2, 3, 4, 5. So pen-3-ene is a bigger number than pen-2-ene. This is cis pen-2-ene. They haven't asked you for the name, but D is cis pen-2-ene. And then E must be the trans isomer, where the two alkyl groups must be in opposite position. I'm just going to draw the CH3 there and the CH2, CH3 there. So I just put the H there and there. When you break the double bond, they are still going to give you the same product. RCH will give you this. The RCH here will give you that, because 3 carbon give you 3 carbon carboxylic acid from the RCH. The 2 carbon RCH give you the 2 carbon carboxylic acid there. Okay. Now compound C gives CO2 and this 4 carbon carboxylic acid. What do I know about compound F? If I draw it as a carboxylic acid, 1, 2, 3, and 4, it could be branch. Do we know whether it's branch or not? We have no idea whether it is branch or not. We just know it's shorter chain hydrocarbon. We have no other information whether it is this, or you could of course also draw the branch isomer, which is this one, because when you have 3 carbon straight chain like this, you can branch it out into like that, and then you will get 2 methyl propanoic acid, or you can get butanoic acid. It's perfectly fine, but whatever you draw there must correspond to the actual alkene. So if I have my actual alkene, I must have H and H, because this CH2, terminal CH2 will give me CO2. This carboxylic acid comes from RCH. The fact that I have H and H, they are the same atom on one carbon of the carbon-carbon double bond. That means I can never have cis and trans isomer. So it doesn't matter where I put the alkyl group on top at the bottom. It really does not matter, because this side already tells me I cannot have cis and trans, because 2 atoms or 2 groups of atoms, they are the same on the same carbon of the carbon-carbon double bond. No cis and trans there. So I want to get 4 carbon carboxylic acid. So this is CH2, CH2, CH3. 1, 2, 3, and 4. So 4 carbon carboxylic acid. 1, 2, 3, and 4. Okay, RCH, carboxylic acid. CH2, give me the CO2. You can also get from this other one. So this one will have come from, if I draw the other one, or F comes from, what is the alkene? Terminal alkene. And then I will have 3 carbon like this. So this is the RCH. So this is carbon 1, carbon 2. Carbon 2 is branch, and carbon 3. So this will be your C if you choose to write this branch isomer of the carboxylic acid. You must get this for C here. But if you do this straight chain, you must get this. There are really no information on whether it is straight chain or branch chain. Just from this alone, we don't know. Okay, we do know it's C4H8O2. This is CH3, CH2, CH2, CO2H. So there are 3, 4, 5, 6, 7, 8, and there are 2 oxygens. This and this, they are what you call chain isomer, and you will see that this one is CH3, CH, CH3, CO2H. So again, there will be 3, 4, 5, 6, 7, 8, 8 hydrogen, 4 carbon, 2 oxygen, just like the formula of F for this one here, because they are chain isomers, same molecular formula, different structural isomer. Between D and E, so D and E must be your geometric isomer, the cis and trans isomerism. Okay. Now propene is an alkene. It reacts with bromine to give you 1,2-dibromopropane. So you know that it will decolorize bromine water. And what you get is you add bromine across the double bond. The type of reaction is what you call addition, as stated in AS introductory. The mechanism is what you call electrophilic addition. Be very careful about the type versus the mechanism. Now they say, how is it carried out? How is it carried out? In the dark? Because if you do it in the presence of sunlight, you might do free radical substitution instead on the alkane. Instead of this addition reaction, your bromine will still get decolorized, but it might react with the alkane instead of the alkene. What is the type of reaction? it is an addition reaction. They are not asking for mechanism. You shouldn't be confused here. You shouldn't write down the mechanism when they ask for type of reactions. Have a look at the AS Introductory Organic Chemistry syllabus there. The very last 2 marks of these questions is all about mechanism, which is the electrophilic addition mechanism. So now they want you to draw the electrophilic addition mechanism. If this is an AS paper, they will probably give you 3 marks or 4 marks already. We need to be careful of what we're doing. So if you want, you can draw a display. They are not so big, but typically I usually just draw my skeletal formula. Doesn't matter. The first thing that happens is the Br2 molecule is actually non-polar, but when the Br2 comes close to the double bond is rich in electron, and they will polarize this one to be delta plus, because this now become electron poor. As this is rich in electron, you want to attack electron poor center there. So the first thing that happens is rich attack the poor. The rich in electron is the carbon-carbon double bond, attacks the electron deficient bromine, and then break away and give the 2 electrons to the bromine there. So everything else doesn't change. But what changes is you have added bromine. Then you have a plus there. But you know better that there could be 2 possibilities actually. That is 1 possible carbocation. But I could also get the other possible carbocation. That is going to be where the carbocation is on the other side. So I'm going to remove that Br there. So what happens is the Br add on the other carbon and I get this. Is there a difference between these 2? There is. Okay, this is a primary carbocation because the carbon with the positive charge is bonded to one other carbon is a primary carbocation. This one on the right is called a secondary carbocation because the carbon with the positive charge is bonded to 2 other carbon. This, however, will not give you a different products. They will give you the same products because you are doing the reactions with a symmetrical Br2. So from the lone pair of the Br minus, attack the carbon. From the lone pair of the Br minus, attack the carbon. The Br minus come from here. The 2 electrons go to Br. You have a lone pair. No charge and no charge. Now a carbocation is balanced out by the charge of the Br minus. So altogether, you are going to get the final product. Let me just copy paste what I did before. So that was what you gotten. And now I am just showing you the other Br adds there. But of course, the other Br could also add there. So, I better just use a same color so that you are not confused about what is happening. So you get the same product whether from this primary or secondary carbocation. But in general, we said that tertiary carbocation is more stable than secondary carbocation is more stable than primary carbocation. You will know this from your AS chemistry as part of the stability of carbocation. This is called stability of carbocation increases as the number of alkyl electron donating groups by inductive effect. They are all as stated in the AS syllabus. Inductive effect is under alkene chemistry, and the stability of the carbocation would increase due to more alkyl electron donating groups by inductive effect. Doesn't make a difference here, but it will make a difference when a question gives you major versus minor product. It's just a very straightforward 2 marks mechanism. I'm sure you won't get penalized if you don't draw the other intermediate, but you still need to show rich attacking the poor, the dipoles, the lone pair on the Br minus attacking the carbocation carbon, giving you the final product to complete the 2 marks mechanism there. And that's the end of that 10 mark question. In this next question, we have the section B type of questions. So section B is no longer relevant in the current 2022 syllabus, but then I will just go through whatever questions that are still relevant to the current syllabus. For instance, in this question 8, we are talking about proteins, and protein chemistry is still around. So is the chemistry of amino acids, and so is the polymerization chemistry. What is the type of chemical reaction? The type of chemical reaction to form this polymer chain. we talk about amino acids that can undergo condensation in order to give you condensation polymer called proteins. So you get proteins because you have polypeptide. Polypeptide basically means many peptide bond. So peptide bond is this amide bond actually, because we get it from amino acid that have a special name called peptide bond. But then if it is just a normal amide, we just call it amide. So what we can say is all peptides are amides, but not all amides are peptides. So be very careful there. So we are not forming a, are we forming a polymer? Yes, we are forming a polymer, but the type of reaction is called condensation because we are forming a condensation polymer. Now the next thing is these amino acids are given as the structure here, serine and valine. So what we know is H2N and then C and then H and CO2H and the R group. This is the general structure of an amino acid. So in serine, this CH2OH is your R group. In valine, this CH3CH, CH3 is your R group. Now you want to draw dipeptide. You want to draw the val and then the SIR. So if I have the val on the left and the SIR on the right, and what is important is they want the skeletal. If they want the skeletal, I cannot draw any other thing apart from the skeletal. So what I do is, I start by drawing the val. So the NH2 wouldn't react, it's the CO2H that react, for instance. So here, I will lose the OH. I will lose the OH in my condensation. Lose the OH, and then the NH2 here will lose the H from the serine because the serine is on the other side. So I'm forming this new bond in pink. This is NH. NH, in fact, I don't want to show the bond there. It's just NH. And then I just complete the other part of the serine molecule. This is the new amide bond that I'm forming because I break this bond there, C single bond O. I break the NH covalent bond as well. And then I'll form a small molecule minus H2O condensation reaction. As I form one amide bond, I kick out one water. And this is part of the val first and then the SIR, even though they have put the serine on the left side, but this structure they want is val on the left and then serine on the right. So there's val and then serine, val SIR. Okay. Now this next question is no longer relevant. This is actually part of biochemistry, but you can think about in the context of intermolecular forces, obviously. So different types of amino acids, maybe I should talk about it. Different types of amino acids have different R group. I just talked about the structure of amino acids earlier, where you have the basic amino group, the acidic carboxylic group, a hydrogen, and an R group. Depending on what R is, it will affect the properties of the protein chains. Different types of amino acids have different R groups. And these different R groups, they can form different interactions with each other. So different R groups will have different interactions. Different R groups form different interactions with the CO or the NH or other R groups further down the chain, because you have a long chain, right? Further down the polymer chain. So for instance, we're going to specify a couple of things. The best kind of answer would be to specify a few things. So example, between CO, delta minus delta plus, and the NH, you can have hydrogen bond. Hydrogen bond is pretty strong, and that is usually what is holding part of the really strong intermolecular forces that holds protein together. What else can you have? You can have between the non-polar hydrophobic. Hydrophobic means they don't dissolve in water because they're non-polar. Alkyl chain. So what you get is you just get the London dispersion forces, which is just van der Waals, all London dispersion forces. What else can you have? I guess the hydrogen bond is just a strong version of permanent dipoles, right? You could also have between the SH and the SH residue of cysteine. So the biology student would know what I'm talking about. This is the one that will give you the disulfide bond. It's actually the chemistry of hair straightening. So your hair curls up as they form the disulfide bond. So you get those really foul-smelling chemicals in hair salons, and those things break the disulfide bond, and they will straighten your hair again by breaking your disulfide bond. Anyway, not that much chemistry there, mostly on biochemistry. This next part of the question, so using label diagrams or words, why a particular enzyme may only catalyze a specific reaction or a specific substrate for 2 marks. This is the lock and key mechanism. This thing remained in the syllabus, in the 2022 syllabus. You will find it under rate of reaction. And under rate of reaction, you will learn this as biological catalysis. So enzymes are biological catalysts. So their catalysis is obviously known as biological catalysis or enzyme catalysis. I'm not a big fan of writing a lot of stuff, I guess. So I'll just write a couple of simple things. So if that is my substrate, let me just pronounce that and write that properly. That's my substrate, so to be metabolized, and this is my enzyme. So what I will get is I will get an enzyme substrate complex, where I just need to move this a bit closer into that. So what I get now is an enzyme substrate complex, and from there I can then get back my enzyme. And I'll get my products. Does that work? Yep. And then I'll get back my enzyme, and I will have form a different product or something like that. So there will be like products. So we're just drawing simple diagrams to show the idea really. So just to show arrows, because we are representing that going to that. This is your enzyme substrate complex. So why does it only work with specific substrate or specific reaction? So we can say that enzymes have active sites. So these are three-dimensional pockets, obviously, that only that have specific shape. And this specific shape allowing only substrate of certain sizes, of certain complementary geometry or complementary shape. So complementary means it must match the shape. That's why it's called lock and key mechanism. Complementary shape to fit in and get metabolized, or undergo a catalysis reaction, or to get catalyzed. So therefore, very, very specific lock and key mechanism there. Now the very last bit here, this is non-competitive inhibition. I'm not going to talk about this. This was actually from the old biochemistry syllabus. In the new 2022 syllabus, in fact, in the 2016 syllabus, it was already scrapped out. You probably learn this in biology rather than in chemistry these days. So, it's a good thing they removed quite a lot of biology from chemistry, because biochemistry has never been my strong point. Okay, so that's the end of that whole question there. This question is about DNA fingerprinting. Again, this is part of the syllabus that has been taken out, so we can skip that particular question. The next bit of the questions. So we have these questions that started out with biochemistry, but this bit is still relevant in the 2022 syllabus. In fact, it was relevant to the 2016 syllabus as well. This is under ionic equilibrium now, no longer under a special topic. It's now under an equilibrium as part of equilibrium constant, because you have partition coefficient. So when you have partition coefficient, KPC, so it is equilibrium constant. So that means only temperature can change its value. So it is constant at constant temperature. That's something you need to know. Representing, what does it represent? It is the solubility. Solubility of what? Solubility of a solute into immiscible. Immiscible means do not mix, and these are solvents. So you're trying to extract it into the more soluble phase, and of course you will always have a little bit of it in the solvent, in which is less soluble in. Otherwise you will not be talking about equilibrium constant, right? You'll be talking about either full infinity or full zero, depending on what is on top. but you don't. You're talking about value. You're talking about equilibrium because they don't mix. There is a little bit of the solute in each of these two immiscible solvent. And this is constant at constant temperature. So it can only change when temperature, at a constant temperature. I think that is the best definition I can think of, at a constant temperature. That seems more right. So it's a fixed value at a constant temperature. Okay. Now the next bit is really all about calculation. Let me see how many marks there is. There is 2 marks to really run up these questions. But let's think about this, all right? So we have a partition coefficient of this pesticide. Let's just call it X to make our life easy, all right? This is between hexane and water. Because they mention hexane first, it's always been something that I learned from Jim Clark's Chem Guide, as well as from his excellent book on calculations for A-level chemistry. So this one is mentioned first. It will appear on the right side, on the right hand side of your KPC expression. I'm not talking about equation, I'm talking about expression, in the sense that I will have X in water, and then this is in equilibrium with X in hexane. This is what I meant by, because there is mentioned first, I'll put the X in hexane on the right side, and because it appears on the right side of the expression, maybe I should use equation. Because it appears on the right side of the equation, I will put it on top of my KPC expression. So what is my KPC expression? My KPC expression will be the solubility of X in hexane. So what is the solubility of it in hexane? Divided by the solubility of X in water. KPC is a value with no unit based on this particular equation there. So I started out with 0.0042 gram of X dissolved in 25 cm³ of water. So 0.0042 gram, and I don't have anything there, so 0 gram. So this is initial mass. Now what do I have? I have volume of water. No, let's not talk about volume of water first. I then add in some hexane, and then that means some of it will go into the hexane. So if I have equilibrium mass, so some of it will go into the hexane. So I will have X gram. Now X gram is bad. So let's say plus Y gram. So you have Y gram now. 0 plus Y is Y. So this is how much has gone from the water into hexane. If you started with this, but you lost Y gram into the hexane layer, you're going to get 0.0042 minus Y. It's now time for your volume, because we're talking about solubility after all. We can talk about mass solubility, which is gram per volume, mass per volume, or we can be talking about mole per dm³. We don't know what the pesticide is. It's better we work in gram per cm³ or gram per dm³. I suppose it's gram per cm³ because the volume here is cm³ there. So the volume in water was 25 cm³. The volume in hexane was 25 cm³. So this is volume in cm³ there. So I guess that thing there is in gram and that thing is in gram, so I can cancel out my gram. Alright, now what do I know then? I know my KPC. This is a lot of space. It's very nice to work with when there's a lot of space. 6.0 for my KPC. So I have 6.0 equal to solubility in gram per dm³. In hexane, which is the one on the right hand side of the equation, so Y gram divided by 25, Y divided by 25. At the bottom, I have 0.0042 minus Y over 25. So just do your math and bring up that thing there. So that will become 6.0 times, 6.0 times 0.0042 minus Y, and that is divided by 25. Okay, that's divided by 25 equal to Y over 25. Because you have 25 and 25 at the bottom, what you can do is times 25 both sides, and you will get rid of that 25. We need to expand the bracket very carefully. So 6 times the first portion and 6 times the second portion. So 6.0 times 0.0042, I get 0.0252, and then I get 6.0y is equal to y. So I get 7y equal to 0.0252 gram. Y, which is how much have been extracted. Y is going to be the mass that will be extracted into the hexane, is going to be y gram. So let this be y. So my answer really is find what is y. Y is going to be 0.0252 divided by 7. I get a very small value. This is 3.6 times 10 to the minus 3. And this is in gram. Is 2 significant figure enough? Well, let's have a look at the question. You are given this data, 0.0042, 1 and 2 significant figure. This KPC, 1 and 2 significant figure. The volume, I guess, 2 significant figure as well. So I guess my final answer to 2 significant figure is totally appropriate given the number of significant figure in the question there. And that's the end of that 2-mark questions and pretty much sum up the whole question, which I skipped pretty much the earlier bit of the question because they were on the the irrelevant biochemistry bit in the new 2022 syllabus.